All right, good morning and welcome in San Diego to SpaceSec, the fourth workshop on the security of space and satellite systems. My name is Vincent Lenders. I'm a professor at the University of Luxembourg and I'm co-chair of this workshop. We are living in an interesting time, so what we call the new space area. So what's this? So previously, the last century, space was mostly a domain of a few national, of a few countries, of a few national actors. But this century, space is now more and more becoming a domain where industrial players and are also academic researchers and even universities are starting to launch and operate space assets. And this creates a booming and interconnected ecosystem environment that is quite interesting. Just to give you just to give you a couple of numbers. By now, today, we have around 10,000 active satellites in space, in orbit. And this number is going to increase quite rapidly over the next years. There are plans to launch mostly LEO, low Earth orbit satellites by companies to create mega constellations. And we can soon expect over 100,000 satellites in space. And already today, there are more than 80 countries that have assets on orbit. So this creates a quite interesting environment. But on the other side, cyber threats are also rising in orbit. And there is a growing attack surface. Basically, threats we have been seeing on Earth, for example, in the internet or on other infrastructure, are becoming more and more now also common, and they are in space assets. There is also the trend to democratize space access with commercial off-the-shelf hardware components and software components, and these will come with vulnerabilities that we know from terrestrial systems. Also, criminals and threat actors that have been active on terrestrial systems are now more and more targeting assets in space. So cybersecurity is becoming a very crucial topic in space. Now, the question is space cybersecurity actually unique? Because we have a lot of experience about cybersecurity over the past, but is the space environment so special that the cybersecurity in space requires unique and new approaches? And if you look at the space environment, it's in fact indeed quite unique. We have extreme constraints in terms of resources, power, bandwidth, and so on. The space environment has a very long life cycles with missions that go over 15 years, for example. It's a multi-domain environment, and it's also used for critical infrastructure, critical services. So does this special and specific constraint make space cybersecurity unique? Because, for example, industrial control systems also on Earth also have very similar constraints. And in fact, this year there was an interesting paper submitted to this workshop, and that we accepted as a paper that deals exactly with this topic. So it's why is space cybersecurity unique? A question that probably you have asked yourself and many others have also. And there is a very good paper that I encourage you, of course, to read, with the conclusion that space has very specific characteristics that are also present in other domains, but in their combination, the space environment is so unique that it requires also unique cybersecurity approaches. And this is also why a few years ago, 3 years ago, this workshop was created, because we believe that the environment is so unique that we need to have a dedicated event to actually discuss the specifics about cybersecurity in space. And what is special about cybersecurity in space is actually two communities that are affected. The cybersecurity community and also the space community. And the goal of this workshop is actually to bring together space engineers, experts from the space domain, and experts from the cybersecurity domain, which is something that rarely happens. If you go to cybersecurity conferences, you will find computer scientists there that work on cybersecurity, but not so many space engineers. If you go to space conferences, it will be on the other side. And these two communities are quite diverse, and they have all their own way of working. But what we are trying to do with this workshop is bring this to a common ground, that we can have a discussion, also collaboration among the two communities with a program as we have today. In fact, we are not alone with this workshop, and over the past years there has been similar initiatives and similar events that came up. For example, the European Space Agency is now also organizing frequently a conference on the security for space systems. There is also SpaceSec, a company, a Swiss-based company that organizes every year different events, mainly to also bring together the industry in space and cybersecurity. And for example, there was also last year a Dutch tool seminar with many of you that are here today that participated, which is an invitation-only seminar where the idea was to discuss about different things around cybersecurity in space. And there has been collaboration between these events. There is no strict coordination, but for example, SciSet papers that are accepted at this workshop are regularly also invited to present at SciSet. So these are the type of collaboration exchange that we have among these initiatives, and also many people involved in SpaceSec are also involved in the other events. So this year's the program and the workshop was organized by myself and Gunes Kara-Bulut-Kurt. Unfortunately, she can't be with us today. She's from the Polytechnique Montréal. She's professor there, and she was doing all the organization together with me. And I want to thank her, despite the fact that she cannot come today, but I want to thank her because if we have such a good program this year, it's our merit. If there are things that have been going wrong, it was my fault, basically. Okay, our main role was to come up and have a paper selection process and review process that is rigorous and state-of-the-art. And what we did, the SpaceSec paper review process was based on a very common approach that we will find in cybersecurity workshop and conferences. It's double-blind, so papers were submitted without author names, and the reviews were not disclosed. And then there was there was exactly 3 reviews per paper that were then the basis for a discussion within the program committee, which led then to a final selection of the papers that we will be having in the program today. So in total, we received 37 submissions, and we accepted from these submissions, we accepted 12 paper, either as short or long papers, and 6 as posters. Somebody asked me, why did you accept our paper as a poster? Because it was submitted as a paper. The issue is that it's very challenging to have 18 papers and presentation in a single day, so it's a single day workshop. So we had to limit because of that, and wanted, but on the other hand, we wanted to have a quite high acceptance rate of 50%, such that we can have as much presentations and content as possible. If you look at the evolution over the last 4 years, We have a growth of the number of submissions since the initial start. Also, more than double the number of submissions compared to last year, which is for me a good sign of the growing community momentum that we have in this area. Also, we were able to, with this approach of accepting posters, short and long papers, we were able to keep this 50% acceptance rate, which is important for us to have as many presentations as possible. So how is it working today? Today we are going to have three types of presentations. We will have long paper presentations. There are 15 minutes talk, including 5 minutes Q&A. We have also short paper presentations, which are 10 minutes, and with 5 minutes Q&A. And then we have poster presentations, which are lightning talks of 3 minutes. And we will have also a poster session where you can walk around in this room. The posters are attached to the walls, and there will be half an hour time to also go to the posters and discuss with the presenters. A small note on the opt-out presentation model that NDSS adapted this year. This is new for NDSS, that when you get your paper accepted, you are no longer required to present it at the conference. You can choose whether you want to present it or not. We took over this model also for SpaceSec. So basically, we asked all authors if they want to present or not. And if they say they don't want to present, we still keep their paper in the proceedings. So the papers are still published, but there is no presentation. Luckily, I mean, we were not sure about this decision because, of course, we were a little bit scared, afraid that some or many accepted papers would decide not to come to the event. But luckily, most of you are here for presentation, and only one long paper, one short paper, and one poster. As you can see here, these decided not to present their work. So you will find these papers and this poster online on the website. You can download and read it, but there will be no presentation from them. So regarding the clusters, so if we look, when we looked at accepted papers, we identified 3 areas where there is a cluster of topic where people are working on a similar topic last year, basically. And I think it's interesting to see. So this is basically topics that are actually important for the research community at the moment. One is about threat modeling, on combined threat modeling between Earth and space. And that's one topic. There is another cluster of accepted works that is on the secure software foundations, so to build secure software for space missions. And the third topic that emerged is resource-aware security, basically developing security that will take into account the resources of the space environment. And around these 3 topics, we created the following program for today. So after my opening remarks, we will have the first session, the first paper session on threat modeling beyond Earth, followed then by the short presentation and poster session. Then we will have a lunch break, and followed by, in the afternoon, by the paper session 2 on secure software foundation, and the last session of the day will be session 3 on resource-aware cybersecurity. And the workshop should close at around 4 o'clock. With that, before concluding, I want to thank many people. This workshop is only possible because of the volunteered work of the community. I want to thank the steering committee of SpaceSec for the strategic vision and also the governance throughout and the support throughout the year. I want, of course, to thank all reviewers that carefully read and reviewed all the submissions. I want especially to thank Simon Birnbach and Jesse Hamill-Stewart, our web chair and also our publicity chair. That did a great job and gave us a good publicity to attract so many submissions. Then, of course, I want to also thank NDSS and Internet Society for providing us this platform, this great platform, and also all the support needed for the publication and the registration. And last but not least, I want to thank you for coming here to San Diego, the authors, and also for presenting your work. Thank you very much. So with that, I will conclude here. If you are on social media, please use this hashtag, SpaceSec 2026, such that we all use the same hashtag. So that concludes my opening remark, and I would like to give the word to our session chair of the first session, Samuel, please.
Yeah, thank you. So our first session, as we just saw, is about threat modeling. So the first paper we have towards automated threat modeling for space systems via SPARTA matrix, Ko-hoon Park from Korea University.
Good morning. Thank you. Thank you for having me here. I am Joonhyuk Park. I'm a master's student in Security Engineering Lab in Korea University, School of Cybersecurity. And I am the author of the paper Towards Automated Threat Modeling for Space Systems via SPARTA Matrix. And I am very happy to be here and present to you my work today. So let's get right into it. So before I start talking about the details of our research, it is very important for me to talk about the background and the why we carried out this research. And it all starts from why threat modeling and cybersecurity is important for space systems. So in the past, the security for space systems were based on, it was met by security by obscurity, which means that we kept the system architecture and requirements secret from the public. This somewhat gave us a false sense of security that keeping something secret keeps it safe from attackers. It keeps it safe from attackers. Well, now the space industry looks completely different because it's not, as Vincent pointed out in the keynotes, it's not just nation states that are deploying satellites and spacecrafts. It's also the private industries. They are deploying their own spacecrafts into orbit. And with the thousands of satellites in the orbit systems, the attack surface is obviously expanding. And we need a more systematic way to secure our space systems. So the paradigm for keeping our space systems safe is through establishing regulations and strong policies, and also conforming to strong standards. One example is the Space Policy Directive 5, which was from 2020. This was the first comprehensive US cybersecurity policy related to security of space systems. Also recently, there was this was published by ISO, Cybersecurity Management Requirements and Recommendations. And These examples all point out that we need to think about security of space systems from the earliest stages of design phase. And specifically, practices like threat modeling is very important. So now that we have the idea that threat modeling is very important for space systems, but how do we do it? Threat modeling is very desirable, but it is very difficult when we do it manually because it takes a lot of time, it consumes a lot of time, and it is very difficult to maintain the consistency throughout the whole process. And therefore, we need an automatic solution for threat modeling. However, up to now, there were no automated threat modeling tools specifically tailored for space systems. And if we were to use the existing tools for general purpose IT systems, which lacks space-specific domain knowledge, we cannot identify domain-specific threats for space systems. So this is where our research comes into play. We developed a domain-specific threat modeling tool for space systems, and we tried to embed the knowledge of space systems into a well-known threat modeling tool called the Microsoft Threat Modeling Tool. It's TMT for short. So for those of you who doesn't know TMT, it lets us identify domain-specific threats by based on modeling our systems into a data flow diagram format, and it lets us define a specific domain-specific template composed of stencils, which are used to actually draw the data flow diagrams, and the tool automatically identifies the threats according to the data flows. So this is an overview of how we built our template for TMT. First, we extracted the space-specific threats from the SPARTA matrix, and then we incorporated the defend and MITRE attack knowledge base to define our stencils and map the threats, map the SPARTA-based threats to our stencils. I will talk about the details of how we did that right after I explain what these, right after I briefly explain to you about what these knowledge bases look like. So first, the MITRE attack framework models adversarial behaviors the MITRE attack framework defines a matrix of TTPs, which are attack methods, short for tactics, techniques, and procedures. They are adversarial behaviors against general IT systems commonly deployed in enterprise environments. And these are, each TTP is mapped to a certain defend artifact and related SPARTA TTPs. So the defend framework defines what's called a defend artifact ontology. And a defend artifact is any object like a file or processes or network connections that can be compromised by specific MITRE attack TTPs. So the ontology itself, it describes how the hierarchy of those artifacts are formulated, and they describe the related offensive techniques to those artifacts. And last but not least, the SPARTA, the Space Attack Research and Tactic Analysis. This also defines a matrix of TTPs, but this one is specific for space systems. And as I mentioned before, each SPARTA TTP is mapped to one or more MITRE attack TTPs. So now I'm going to explain about the the specific processes of building our template. So first, we defined the stencils, which are system elements for space systems. We first identified the initial set of space components based on specific architecture documents provided by NASA and other other authorities. And second, we mapped the properties of defend artifacts to those stencils based on the DAO semantics to enable precise threat identification. This is because the DAO, they describe a standardized view of what the components are and how they can be compromised, which we needed to map the threats to the stencils later on. And since we were building upon TMT, we mapped the basic stencils to the data flow diagram elements, such as processes, data store, and external entity, and so forth. So this is what our stencil looks like in the actual tool itself. As you can see, there's a list of stencils, which is on the left side. And then for each stencils, there are specific properties which users can manipulate as constraints, which is based on the defend artifact ontology. Next, we go on to how we refine the threats for space systems. We first extracted threats from the SPARTA matrix, the TTPs itself, and they are embedded into our tool in the sub-technique levels. So this is probably the most challenging part of our research. It was encoding the threat generation expression. This is ultimately where we use the SPARTA MITRE attack and defend logical chain. So we had, as I explained before, we had the specific DFD stencils, which is based on the defend artifact properties, and we had the threats extracted from SPARTA. Now we had to link those two together in order to for the tool to identify the threats based on the DFD. So since the MITRE attack MITRE attack matrix was mapped to both knowledge bases, we used that as a bridge to link the stencils to the threats. So this is what the threats look like in our tool itself. As you can see, there are a list of threats on the left side, and they each threat includes a threat generation expression section. So the tool references that part to identify which part of the data flows are vulnerable to specific threats. Now let me introduce you to how our tool effectively identifies the threats. We used the case study of the Viasat hacking incident in 2022. So we modeled the incident into a data flow diagram format, as you can see in the middle box. And then the tool, we obviously used our template to do this. And then the tool automatically identified the threats, as you can see on the right side of the slide. So these are the screenshots from our evaluation. As you can see, we drew the data flow diagram, and the tool automatically identified the threats like so, and it also generated a threat report. And to evaluate that our tool actually effectively identified the threats correctly, we used this evaluation method. So we modeled the Viasat hacking using our template and also an existing tool called SecOps TM from OWASP. We use this tool because it identified threats on the TTP level, and also we compared the threat list with the ground truth, which was derived by threat modeling professionals. So this is the framework we use for the evaluation. As you can see, our tool covered all the ground truth threats derived by the professionals. But the existing tool only covered a few of those threats. So what this means is that our tool quantitatively, our tool excels in identifying the specific threats quantitatively, but also since it has the knowledge of space systems, it can identify specific threats also. And the existing tools for general purpose IT systems are not suitable when directly used to threat model space systems. So that brings us to the conclusion to our research. As all studies do, our research also has the limitations. So using our template, it might over-detect some threats for space systems. And also some threats that were specific to ground segments were not fully covered in our template. So for future work, we will try to integrate the MITRE ATT&CK framework directly for threat elicitation for ground systems. And to wrap up, our contributions are that first, we suggested the first space-specific domains, domain-specific automated threat modeling tool for space systems. And to build that, we integrated well-known cybersecurity knowledge bases such as SPARTA, MITRE ATT&CK, and DEFEND. So that's it for my presentation. Thank you for your attention.
Questions? If you have a question, come on up to the mic, state your name and affiliation, and ask up.
Rob Cunningham from the University of Pittsburgh. In working with these various other frameworks, can you comment a little bit about how well they worked for the space domain? Was there anything that they were missing? Was something not particularly well aligned? I'd like to hear how your experience went.
So when we were, there was a part where I explained when we were trying to map the threats to the stencils, some specific SPARTA TTPs were not directly mapped to the MITRE ATT&CK TTPs. So we couldn't really link there were some parts where we couldn't directly link the SPARTA TTPs to our stencils. So in that case, we systematically researched some kill chains based on the SPARTA TTPs. So we went over some papers and documents, and we were able to find out the links between those two. So that was probably the biggest challenge of our research. Thank you.
We have time for maybe one more question.
Hi, Jeremy Epstein, Georgia Tech. Can you go a little bit further into a specific threat that you modeled? I'm having trouble going from the abstract of what you were trying to do into something more specific.
Can we go back to the slides? Thank you. So this is one of the threats that we embedded into our template. So it's in the SPARTA TTP matrix. It's called the replay of command packets. And as you can see in the include section of the table, it has specific generation expressions. So when the target is the generic space system process, and it is running on space segment, and the data flow to that stencil carries command, it's set to yes. The data flow itself crosses the generic trust line boundary. The tool knows then if a user drew a data flow diagram according to that specific thread generation expression, then it pops out the thread and says that this data flow is vulnerable to that specific thread.
Let's thank our speaker again. Our second presentation was Temporal Risk on Satellites, team from George Mason University.
So, hello everyone. My name is Shiqi Liu, and I'm a PhD student from the Center for Secure Information Systems at George Mason University. Today, I'm going to present my paper, Temporal Risk on Satellite. So, the threats in space mainly happens in three main segments: the Euroground segment, the link segment, and the space segment. And on the ground, the attackers can break into the ground network or just compromise the user terminals. On the link segment, they can just jam the signals or spoof them to cause confusion. And in space, they can just gain unauthorized control or just exploit the firmware vulnerabilities on the satellite. So our observation is that when the threat occurs, matters not just where it happens or what it is. So in space, the environment changes over time. Unlike on the ground, that we're seeing this almost the same all the time. So the line of sight, the line of sight is sunlight, and the radiation can all shift. And many of these changes are predictable. That's our second observation. Because we can calculate the communication windows and the eclipse periods and the SAA passes from the orbits and estimate the radiation levels from the space visor. So in space security, we often score risk in a very static way. Tools like SPARTA ask experts to score the attack's likelihood and the impact, and then place it in a matrix to get the risk level. So the problem is these frameworks usually ignore when an attack happens and how the operational environment changes over time. So this creates three main gaps. The first one is incomplete likelihood. So we fail to capture how the difficulty of an attack changes across different time windows. Second is the impact underestimation. With a static average will hide the short critical periods where attack could be catastrophic. And finally is the misaligned defenses. So without knowing when the risk is the highest, we cannot deploy the protections very effectively. And to solve these gaps, we introduce temporal risk assessment, which treats timing as a primary concern. The core of the approach, as you can see on the left, is a discretization process. Instead of treating a continuous timeline as one uniform block, we divided the timeline into different time windows, like the sunlight eclipse or geomagnetic storm. And because the physical environment changes and the risk changes with it. So therefore, as you can see on the right, our framework completely discards the idea of a single static risk score. Instead of, we generate a series time-indexed risk matrix. And to evaluate the temporal likelihood, we introduce the temporal adversary capabilities, which describe how attackers exploit time and changing conditions. We capture 5 capabilities in the table, like actuation, forecasting, sensing, synchronization, and hiding. As you move up to the tiers, the adversaries combine all of these, from the script kiddies who can only act in a window to the top state actors who can predict, sense, time the actions and blend into noise. So temporal exploitation difficulty is another key factor to measure the likelihood. It means how hard it is to exploit at the right time. It comes from the 2 parts. The first part is the intrinsic properties, based on the orbital visibilities, like how long a window lasts, how often it comes, and how predictable it is. The other part is the scenario-specific constraints. It's based on the attack goal, like to match an uplink with a critical mission phase. And we show this case study on star melt attack on a LU constellation. And shown on the left, the attacker can flood the satellite with violet traffic. So it cannot enter the sleep mode, which means this drives high CPU usage and high resources draw, which slowly drains the resources like the battery. So in a static framework, like SPARTA, as you can see on the right, it is mapped to the violet command and scored as a high risk, with the likelihood 5 out of 5, and also the impact 5 out of 5. But it does not show how the risk changes with the time. In our work, we split the timeline into the sunlight and the eclipse phases. The eclipse windows normally are shorter, so hitting the timing is harder, which means the higher temporal exploitation difficulty and a slightly lower likelihood. So we score the likelihood of the sunlight is 5 and the likelihood of the eclipse is 4. In sunlight, solar powers supports the system and recharges the battery. So the attacker is mainly basically a performance hit. So we just score the impact as 2, but things will be different in eclipse. The satellite runs on battery, so keeping it weak drains the power and very fast and can push it to the safe mode. So we score the impact of eclipse as 5. So the risk score, as you can see on the slide, the risk score of the sunlight is 16, and which is medium, and the risk score of the eclipse is 24, which is the high risk. This is different from the SPARTA framework we just talked about, which gives one high score for the whole orbit. And with this view, we can focus monitoring and limit during the eclipse and avoid resource wasting in the sunlight. Here are some key takeaways. So the first one is don't treat space risk as static. And timing is also a capability for attackers. And timing constraints directly affect the likelihood of the risk. And the last one is time-aware scheduling can be a mitigation. So thank you. Any question?
Questions? Maybe while some folks think about some questions, I have one question.
Okay.
So the idea to slice the system into different times and look at how risk varies is interesting. I guess my big question, though, is how do you decide when to do that slicing? Like when to define different time intervals? Like, it seems in some examples, some partitions make sense, but not in all examples.
Mm-hmm. So you mean how to divide the timeline into the specific time
discrete
windows?
Intervals.
From now, we just define this problem as an expert's job. Experts can divide this timeline into the time windows based on this expert's background and knowledge. And maybe in the future we will find a way to automatically to divide it. Yeah, thank you.
Sure. One more question.
Hi, interesting talk, Sam from MIT
Thank
Lincoln
you.
Laboratory. Just curious, once an operator has this temporal risk sort of mapped out, after addressing Sam J's question, what do they gain from doing that? So for the example you showed with the eclipse, wouldn't you want to have a defense to prevent those valid replays of commands always? When would you turn that defense off?
So with this risk framework, it will let us to focus on, pay more attention on the eclipse time and put more resources on it. And during the sunlight, we can do not do so less constraint on the protections. Just let the normal data uplink and download. Yeah.
Okay, thank you.
Thank you.
Speaker? Let's thank our speaker. Our third presentation in this session is risk assessment for ML-based applications in satellite systems from Ben-Gurion University of Negev.
Hello. Hello, everyone. Thanks for having me here, first of all. My name is Simon Shigol, and I'm a master's student in CBG Labs in Ben-Gurion University. And today I'm going to present our research about the risk assessment for a machine learning-based application in satellite systems. Okay, so let's start from the beginning. Nowadays, we're in an era of converging of several, an advancement in several vectors who are allegedly separate and not connected, but we will talk about their intersection in our presentation today. First of all, if we're looking at the satellite advancement in the past years, we can go back from the older days where satellites were analog machines with deterministic logic, towards to software-defined missions and satellites. And nowadays, as in many other technologies, we witness the integration of artificial intelligence and machine learning in satellite system as well, which leads us to the next vector, which is the advancement in the ML progress over the years. When we started around some dozen years ago with early concepts such as regressions models, and later more advanced models such as reinforcement learning and deep learning. And today we witness the machine learning systems running on edge devices such as satellites. When we used to, and the next vector is the cyber threat landscape. When we used to talk about cyber threats, in the early days it was mentioning the physical threats, jamming threats, and later on software bugs which were exploited for attackers. And nowadays we're advancing towards a new threat emerging, which called adversarial machine learning, which also catches us with the other vector intersection in the space domain. So first of all, why are we talking about machine learning at all? We know that machine learning is in most technologies nowadays, and it's a sort of a buzzword, but it is a universal technology which we meet today in applications from the e-commerce domain and to autonomous vehicles and satellites, as we know. And why in satellites we see these machine learning applications? Because as was previously stated, nowadays we talk about mega constellations, and in mega constellation you have to use planning and synchronization in real time, and that's why you must elaborate with machine learning. You have several limitations and several characteristics that are unique for space, as mentioned before, as limited bandwidth and long latency, which can affect the mission itself, and that's why machine learning is based in many different applications in space. These are some examples, but we'll dive into some more, such as beam mapping, anti-jamming, which maybe are applications that you heard about and know about, but you didn't know that machine learning stands behind it. But nowadays, machine learning, as I said before, is almost in everything. The problem is when a satellite is learning, it can be taught wrong behavior. And that's why we addressed the threat of AML, adversarial machine learning, which I soon will explain what it is. So first of all, what is the adversarial machine learning I'm talking about? If I want to deploy a machine learning model nowadays, we use a basic and general pipeline, which involves the preparation of the data, then the training of the model, and eventually the deployment of the model. But it's a bit more complicated than this, because each of these steps has several steps in it. And actually, each one of these many steps is an entry point for an attacker to attack the machine learning model and the pipeline, and therefore attack the application itself on the edge. What are the attacker's objectives? So as all of you know, in cybersecurity, we talk about three main objectives: the integrity objective, availability, and privacy, where integrity attacks can perform in satellites as processing and prediction of incorrect predictions and eventually affect the mission itself. Availability, which is a very big risk for a satellite because of real-time systems that get attacked and damage and degrade the model performance and cause resource latency. You can understand it causes many problems in the mission itself. And privacy attacks, which are less common in the satellite domain, but it's the ability to extract the model or the data and so on. Each of these objectives has several mapped feasibilities or capabilities of an attacker to approach these objectives. These, as you can see, is mapped by a taxonomy made by the NIST Institute in a publication from 2024, I think. And they mapped several capabilities that an attacker can attack and go through them to create several different attacks. Also, this taxonomy is talking about the attack families themselves. We see attacks such as poisoning, such as evasion, energy latency, and so on. So all of these attacks are available by an attacker having the specific capabilities to perform this attack in each of the steps along the pipeline of the machine learning. We can see it from early stage attacks such as poisoning attacks, which talk about poisoning the data the model is trained on, and eventually evasion attacks that happen in the inference phase. And these are just examples to attacks in the domain of machine learning attacks that can be used to attack machine learning models. So if we'll try to talk about some real life example and the use cases we'll know. So if we'll talk, for example, about autonomous vehicles, if I have a Tesla and it has a machine learning model running on it to detect and classify the object it sees, it's a real application of a machine learning model on an everyday system. If an attacker wants to attack the integrity of this model, and for example, he has a capability of reaching the testing data control, he can actually perform an evasion attack during the inference time itself. And for example, by putting an adversarial perturbation on a legitimate sample, it can make the model think it encounters a yield sign, which we all can understand how it can affect the physical problem in the real world. But you can also take this and look on the implications of it in space. And actually, this was the domain we decided we want to dive into. So our work was based on the framework. Yes, that's a framework that assesses risks on machine learning based applications in general. And we understood that there is, because of the previously stated constraints of satellite applications, we need to make an adjustment of a framework to be fitted for a satellite domain. In general, how the framework works, so basically it's a pipeline starting from the profiling of the system. The system is the ML application of the model the user has in his use case. So the system profile the machine learning use case by asking the machine learning engineer several questions and eventually map the attacker capabilities that an attacker can elaborate from the building of this specific model. It uses it uses a success rate factor that is reached by several scientific and technical reports in a certain data set, and an algorithm that is based on a mapping of different feasibility factors of an attacker to known attacks, around 90 attacks that are known in this world of machine learning, and impacts that it can cause. And eventually, you get the tailored risk profile with a ranking of your attacks that your model is exposed to. Okay, so our methodology was, first of all, we wanted to map which machine learning applications we have in space, such as anti-jamming, beam hopping, and the other examples we see and we will see later. Then we mapped the threat actors and the attacks relevant in the space domain, adjusting the framework by adding different parameters that are unique to space. We evaluated several representative use cases which were spread along ground-based models, satellite-based models, etc., and eventually analyzed the results and offered several mitigations. So the first part was mapping the machine learning applications in space. We understood by reading the literature that there are many different machine learning in different maturity levels nowadays. Okay, we understand that it's in the space domain. It's something that is pretty new, and it's not yet implemented in production phases. Many of these applications are applications that we saw in research test beds or research satellites. Then we took those applications and mapped the application to, on the layers of the satellite in which segment they are running. And then we took these applications and we started to map the threat actors themselves. So we understand that in space we have different threat actors, and especially, as mentioned before, nowadays when we see that not only state-sponsored satellites are in space, but there are also research satellites, commercial satellites, and nowadays it become more and more democratized. We understand that is this also a factor when calculating the risk over a satellite application. Next was mapping the attacks. So we understood from the literature that there are several attacks. We try to cluster it by themes, communication-based attacks, model manipulation attacks, and so on, and to see in which use cases these attacks come to be more significant. Later, what we did was deciding which parameters we want to add to the framework itself. It was actually opening the algorithm and adding several parameters that are unique to space. Eventually, as I said before, the framework was addressing a general machine learning application risk assessment. But here we thought there are three main issues that should also be addressed. The first was the deployment segment. We understand that an ML model that runs on the user segment is much more vulnerable than an ML model that runs on the bus layer, for example. The other one was the orbital regime. LEO satellites were much more much easier to attack. Not much, but it was easier to attack than GEO satellite constellations. And eventually the ownership, which also states the defense it has and the cyber hardening that happened in the training phase. We took several use cases, diverse use cases. Some of them were ground-based, some of them were space-based. From the domains of anomaly detection and beamforming, etc. And each one had its own characteristics. And eventually, we took it to the framework, to the adjusted framework, and ran them through it. And we got different results. We got different ranking of the families and objectives of the attacks. And we try to take some insights of it. So the main insights were that, of course, integrity and availability risks are the most focused ones in the satellite context. We can understand it because, again, when we talk about real-time systems, the availability is a big factor. And also the integrity because, as I said before, all the mission is affected if the data is incorrect. We offered several mitigations that are mitigations from the world of general adversarial machine learning, but here they were mitigation that let us see better results after amplifying them and run this again through the questionnaire. Adversarial retraining, which is basically train the machine learning models with deliberately poisoned data so it can understand that be more robust, and some other mitigation. It's expanded in the article itself. And last one, so conclusion, we understood that there is some future work that we think we should do and we want to do. I mentioned it here, but because of time, I will go further. And that's it. So thank you very much. And questions?
Any questions?
Hi, I was wondering if the onboard computation capabilities of the satellite chip was something that you took into consideration when you mapped the attacks?
Yeah, so as I mentioned before, some of the use cases were onboard use cases, which inherently, when profiling the system, so the profiler, the ML engineer in this case, he can state whether it's deployed onboard or deployed on or ground-based, and it takes into consideration in the algorithm of the calculation itself. Okay, thank you.
Maybe one more question. Well, I have a question.
Yeah, sure.
So you had a couple different ways of slicing your results there at the end. The one that I was kind of expecting but didn't see immediately is like, which application of ML on space systems is inherently the most dangerous, effectively? Do you have thoughts on that?
Yeah, so thank you for the question. As I can show it here, we had to cut it in a certain way, okay? So the way was looking at it through the attack type and the objective, okay, along the use cases. But the use cases in this case are just the representative use cases, and there are around 15 ML use cases we found. I think I would say the whole world of optimization is a world that nowadays is using ML, and because optimization is the beginning of the whole process of all the space missions, so it can affect much wider and have a bigger impact. So that's what I would say.
Thank you. Let's thank our speaker again. Okay, and our last presentation in this session is Orbital Escalation, Modeling Satellite Ransomware Attacks Using Game Theory. And Efren Lopez-Morales from New Mexico University is going to be presenting that.
Good morning, everyone. My name is Efren Lopez-Morales. I am an assistant professor at New Mexico State University, and I will present orbital escalation modeling satellite ransomware attacks using game theory. So ransomware is a big problem. We haven't gotten rid of it. In 2025, for example, 49% of victims paid the ransom to get their data back. The average ransom payment was $1 million. And 50% of these attacks targeted critical infrastructure. So satellites are obviously critical infrastructure, so it is a possibility that they will be targeted by a ransomware attack, but it hasn't happened. So as we saw in the beginning, satellites have special properties talking about cybersecurity. So for example, they take years to commission and launch, especially MEO and GEO satellites. They are becoming increasingly vulnerable. That is why we're all here. And you have very limited or almost zero physical ways to recover a satellite. So is this even plausible? So I will argue yes. In 2023, you have this paper called WannaFly, where I think it was Gregory Falco and his group, they did this attack where they flooded the bus of the flight software with messages, effectively stopping the communication inside the satellite. But as one important thing, at least for my paper here, for my model, is that the ransomware for satellites doesn't necessarily depend on encryption. So it's not game over like in, if they encrypt your hard disk, it's very difficult to recover it without the key. So this opens other strategies for recovery. So last year, people were already asking this question. If a satellite is held for ransom, will we have any choice but to pay? And their argument is that there are very limited options talking about policy. So in this paragraph from the article, they explicitly say that there are no major space policies talking about ransomware, even though we know that this happens almost every day on Earth. So the question is, what if you're a satellite operator or owner, what do you even do? Do you pay the ransom? Do you attempt a recovery procedure? Do you know if there is any recovery procedure? Or you wait to see maybe next pass is already gone and pray. So to answer some of these questions, this is where I introduce this model called the orbital escalation game. This is a game theory model with the following characteristics. First, it is so the most important thing is that the pace of the game is dictated by the orbital pass. The second characteristic is that the attacker escalates the ransom every time there is a pass, and the defender chooses a strategy. I'm going to talk more about the strategies, but that's what it is in a nutshell. And another special feature is that in game theory you have different frameworks, and this particular game, it's a Stackelberg game. And a Stackelberg game is a sequential game, so it is not like the famous Prisoner's Dilemma. That is a one-shot game that when every player implements their strategy simultaneously. So this is not that. This is a sequential game where one player does something and then the next reacts and so on and so forth. So now I'm going to describe the model in detail. You have two players, the defender, which is the satellite owner, and you have the attacker, which is the ransomware attacker. Then you have, for the defender, you have 4 strategies, which are pay the ransom, refuse to pay the ransom, restore. Restore can be broken down into multiple restore procedures like save mode, some telecommand. And then you have idle. Idle means that you don't do anything directly, but it gives you time to say, for example, call the government, call your insurance company, something like that. And then the attacker only has 2 strategies, which is to set the ransom to some amount and to set the escalation policy, which is how much the ransom will increase at every step. The payoffs, so the whole reason these players are playing this game is that they want to get something out of it. The defender wants to minimize the expected cost, and the attacker wants to maximize the payoff, so how much money they get. And so the information set also is something that we have to define for the game theory model. This particular game has perfect information for each one of the players, and there are important limitations that this brings, and I will actually address this in the limitations part. But just know that in this particular game, everybody knows everything about the other player. Okay, so now parameters. These are, you could call them economic parameters. So for example, the defender has to worry about what is the cost of the restore procedure. For example, if you are doing save mode, does that cost you something? The duration. If you are doing save mode to recover the satellite, how many passes does that take? 1, 2, 3? What is the probability that these procedures will succeed? Probability is just from 0 to 1. And the downtime cost is the cost that the money that you're losing because the satellite is not doing whatever it's supposed to be doing. And finally, the satellite loss is just the cost of losing the satellite. For the attacker, you have the initial ransom, just some amount of money, the ransom escalation, the exploit cost. So in this model, the attacker has to pay some money for the exploit. It could be 0, it could be $1 million, depending on if the exploit is new or not. And then they have to pay a holding cost. The holding cost is just, for example, if you imagine like a state-sponsored actor, they have to pay electricity and all of that. Or in this holding cost, you could include some monetary amount to account for the risk that you will get caught. You can do a lot of things with that. So, okay, and then another important concept here is the concept of the horizon. So in a Stackelberg game, you always have to have a horizon, which is you have to somehow determine when the game will end. And in this particular game, the game ends at some end passes. And the way the players control this is, for example, the defender can pay, refuse, or restore the satellite operation successfully. That will end the game. And the attacker can give an ultimatum to the owner saying, you have to pay this money by, 2 days, and those days are 4 passes or something like that. That sets the horizon of the game to that number. Okay, so I just described the game to you. So how do you play the game? The equilibrium is basically the method to play the game to the best of your ability for the defender or the attacker. So to get this equilibrium for this particular game, we have to do 3 things. We have to calculate the defender's expected cost, the attacker's payoff, and then we have to use backward induction and a Bellman equation to solve the equilibrium. A Bellman equation is just an equation that divides a big problem into smaller problems, and backward induction is a method used specifically for Stackelberg games to solve the game from end to the beginning. So you work backwards, not forwards. It's counterintuitive, but that gives you the best strategy. Okay, so this is a game theory paper, so you're going to have to bear with me with this equation at 10 in the morning. So don't check out. We're going to go through it step by step. So VK is the defender's expected cost at a particular K orbit. So you have orbit 1, 2, 3, so K is that. Then you have 4 options, right? So I told you that the defender has 4 strategies, so each one of the strategies has its own cost. So, and the defender wants to minimize the cost, so that is why you have minimum there. So the first option is to pay, and that means to pay the ransom at that particular pass. Then if you idle, you have to pay your downtime cost, and then you have to pay whatever is the cost of the next pass, because you are just doing nothing. Restore is a more complex one. So this one is an equation within an equation, and here you want to minimize the cost of the J. So J stands for the list of restore procedures that you have. You can have 1 or 10 restore procedures. And then there is a cost for each J. There is a downtime cost multiplied by the duration of the recovery procedure. And then you have the probability that it will fail. So 1 minus the probability that it will succeed, multiplied by the cost of the next pass. And finally, you have the cost of losing the satellite. So you do all this calculation at every pass, and you select the one with the less cost. And that is the defender's expected cost. So, and then the next equation is when you reach the horizon, basically you reach a point where the game has to end, the defender has to make a decision. The decision is, do I pay the cost of losing the satellite, or do I pay the cost of the ransom with all the escalations applied at that point? Okay, and this is the last equation, I promise, and this is the attacker payoff. So everything I told you before was the defender. For the attacker, this one is more passive. So basically, if the defender wants to pay, then the attacker just gets the money. If the defender wants to idle, the attacker has to pay some holding costs, electricity, et cetera, and they get or not get whatever is in the next pass. For restore, they have to pay the holding cost for the duration of the restore, and also they have to pay the cost of the next passes multiplied by the probability that the restore will fail. And if the defender refuses, they just don't get anything. Okay, and then, right, so you use all these formulas to use the backward induction. So I'll just continue here. Okay, so I just explained to you the game. I explained to you how to get the best strategy for the game, and I'm going to give you an example of the game. And for this one, I use a GPS-3 satellite. This is a fictional ransomware attack. But the reason I selected the GPS-3 satellite is because there is some good amount of information on the internet that allowed me to plug some semi-realistically numbers, so that, you know, how else am I going to do that if I don't have some numbers to go on? So let's get in. Oh, what happened? Oh, sorry. Okay, so the GPS-3 constellation is managed by the US Space Force. And so every pass that this satellite is operational, they lose $3 million. They have two restore procedures, safe mode, and privileged telecommand. I just came up with this. So I'm not sure if they have, well, I'm pretty sure they have safe mode. I'm not sure if they have a special telecommand. But they have two restore procedures. And safe mode takes 2 passes, and privileged telecommand takes 1 pass. Safe mode has 0.9% of successful probability, and the telecommand has 0.4. And if the satellite is lost, the US Space Force loses $450 million. Okay, so on the other side, you have this APT group, a fictional APT group called the Filers, and they set the ransom to $112.5 million. Every pass, they escalate $6 million. They had to pay $14 million to develop the exploit, and they have to pay some $0.01 million for their operations. And the horizon is 4 passes because they just tell straight up the US Space Force, either you pay us at 4 passes or the satellite is lost. So again, backward induction, we start from the end, not from the beginning. At the end of the game, the US Space Force has to decide, do I lose the satellite, or I pay the $136.5 million of the ransom at that point? So the best strategy in this model, I'm not saying this is true for every occasion, in this model, the best strategy is to pay the ransom. Okay, and then at pass 4, which is the last pass, the defender evaluates the cost of their options. And here, for example, safe mode is not possible because safe mode takes 2 passes and you just have 1 left. So safe mode is not possible. And the cheapest one is to use the special telecommand. And that is the best strategy at pass 4. At pass 3, these are the numbers. And you can do safe mode because you have 2 passes ahead of you. And you can select the cost of safe mode. So this is the best strategy at this point. And this is the summary. So this will be the actual equilibrium for this particular instance of the game. And you can see how much the defender has to pay at each stage and what is the best strategy. So here I just want to introduce 2 concepts really fast. There is the concept of ex-ante and ex-post equilibriums or equilibria. Basically, it means that ex-ante is before the real-world events have happened. So, for example, if you're talking about probabilities, you're talking about ex-ante because we don't know what will happen. And then you have the ex-post equilibria, which is when you actually observe the events of the game, and you have some concrete numbers. So everything that I have been talking about is ex-ante. And now I will show you some actual concrete example for the game. So here is this scenario. I just came up with it because I think it showcases the game. So in the first pass, because the anti-equilibrium says that you have to do safe mode, then that is what you do. And these are the amounts. So for example, the ransom at this point is 112.5. The defender already lost $3 million because of the downtime. The attacker already paid $14 million for the exploit. And then on the second pass, the safe mode is still implementing because it takes 2 passes. So the defender loses more money, the attacker loses a little bit of money. So at pass 3, safe mode failed, so it didn't restore control to the satellite. So the next thing you can do is use privilege telecommand. And then, yeah, those are the numbers. At this point, the defender lost $9 million. The attacker lost that amount. And then at pass 4, the telecommand succeeded, and then the U.S. Space Force is happy. The game ends, and the ransom would have been $130 million, but they don't have to pay it. So at the end of the day, the defender has to, the expected cost for the defender is $9 million, which is just the downtime, and the cost of the implementation of the restore procedures, and the attacker lost $14 million. So even though $9 million seems like a lot, it's way better than paying the ransom or losing the satellite. And do I have more time? Okay, so the real-world implications, operators have to be ready. They have to increase the contact opportunities, and they can implement this game in their training. Limitations of the model: perfect information set is not realistic. Not everybody knows everything about everybody. Only applies to Leo and Mio. Rational assumption: the attackers might not want money; they just might want to destroy your satellite. Discrete passes: you can change the passes to seconds or minutes. And then on future work, you can do parameterization, constellations, Bayesian extension for partial knowledge. And in conclusion, I present the first game theory model to model the ransomware attack on a satellite. And it encodes 7 economic parameters. And I provide the GPS-3 satellite case study. Thank you for listening.
Okay, we have time for maybe one question, if somebody's got one.
So first of all, I like this talk a lot. Very nice work. A small question and an observation. I think you're assuming that the defender still can retain enough control of the satellite that even though the attacker has succeeded in grabbing control, you can force into one of these recovery conditions. Do I have that right?
Yes, that is right. That is actually written in the paper, but I guess I didn't mention it here, but you're right.
Okay, so here's the scary thought, and then a policy question. If I were an attacker, I could also use this approach to optimize how much money I want to charge.
Yes.
And so the question then is, if you're the defender, what sort of information should you hold back so that the attacker can't do that optimization process?
Good question. So that goes to the Bayesian game extension. I think the first thing that occurs to me is to not reveal where are your ground stations, because if you have more ground stations, then you have more opportunities to try something. So that's the first thing. Another is to hide, to somehow not make public how much is the cost of you losing the satellite. Because I didn't talk about it here, but one of the strategies of the attacker is that the attacker sets the ransom to something like half of the cost of the asset to make you pay. Because if you set the ransom to, I don't know, 95% of cost of the asset, then I'm just not going to pay you, because what's the point? So if you can hide the cost of your satellite, then the attacker can have a harder time trying to set the ransom that would make you pay.
Let's thank our speaker again. We're out of time.